So in our previous video, we were looking at patterns ending in 101, and in particular, we wanted to generate some information about if we have binary numbers of length L, what are the total number of patterns of binary numbers of length L, and how many of those numbers will have this 101 at the end, right? And we found out that it was a quarter. We'll reduce immediately, and so here I've got a worked example with 6 digits. So 2 to the 6 minus 2 gives us 2 to the 4, so 16 total odd patterns. And we know a quarter of those will collapse immediately, which gives us these 4 here. You can see they're all ending in 101. And then for this category of numbers, the ones that will possibly collapse, right, they end in 01. So 2 digits are removed. And it's a question mark whether or not if we add 1 digit, the number collapses. And if we add 2 digits, the number is stagnant. And the total number of digits is the same as it was before we fed it through the odd Collatz steps. So here I've taken this number here, 101001, and I've performed this doubling step and adding it to its double. And that gives us this binary addition. We have 2 zeros that we remove, and we only added 1, so our new number has 5 digits rather than 6. So this number will collapse under the Collatz conjecture. And then if you take a stagnant one here, right, like if you take this 1, 1, and then you add it, right? There you go. You get 0, and then we add 2 here plus 1. Then you get this new number, 6, right? So you've got these 2 zeros, but again, you're going to strike them off with the n over 2. So the next odd number that you feed in has 6 digits here, right? So this one is stagnant, so it's got this blue check mark. And then there's a number of other possibilities. So first we have, 4 numbers ending in 0, 1, 1, right? And so these are possibly grow, right? So you've got, just iterate through. So you've got these ones, and because you have this 1, 1 pattern here, you're only removing 1 digit, as I showed earlier. And then on the front, it's a question if you're adding 2 or adding 1. So either you're stagnant or you're growing, right? And I won't run through the math. You can check it if you want. But that one happens to be stagnant, and the other 3 grow. And then the last set that we have all end in 111. And this isn't a category where all grow. It's actually the same as before because you're always removing 1 digit, right? And there's the potential that you might only add 1 digit, right? So this is shrink, stagnant, grow. And so one thing I want to point out is that there's a very nice symmetry in the total number of numbers. So we have 6 that shrink, right? We have 4 that are stagnant, and then we have 6 that grow. So this splits very nicely, right? And these predictions are the predictions that we can make before the first pass through the Collatz function, right? So this is how they're going to behave when I chuck them in to the black box, that, well, not the black box, but into the box that is the Collatz function for the first time. So yeah, 6 are gonna shrink, 6 are gonna grow, and 4 are gonna be stagnant, right? So if I wanted to find out what happens to the 6 that grow, I would look at patterns for 7 digits. If I wanted to look at what happened to the 4 that are stagnant, I would run these 4 numbers through, and then I would look at this chart again, and I could say, oh, well, some will grow, some will shrink. And then these 6 ones that shrink, or maybe, the other option is some remain stagnant, but these 6 that shrink, I know they're going to reduce under the Collatz function, so I sort of don't care about them. I think in the next video, I'll sort of go into a bit more detail about how these numbers behave, well, not behave, but what happens to these totals as we move up and down the number of digits in the number. Do the growing ones keep growing, or do they appear to keep growing, or do they start shrinking or stagnate, or what happens there?